Good day, ladies and gentlemen. This is the lecture for 7 May. So we've ended off the last lecture and there were some questions about NAND and NOR. So I've included that from Appendix A. So only this stuff that I do in the slides here is of importance from Appendix A and will be included for test and exam purposes for Chapter 4. Okay, so what do we already know about these logical gates? We know it's an electronic device and it normally takes 1 to n inputs and it creates one output. However, in this chapter we use gates with only 1 or 2 inputs. So can you recall the gates that take only 1 input is the NOT gate, and the rest of them, the AND, OR, NOT, XOR, the AND, OR, the XOR, and then today the NAND and NOR, those take 2 inputs. So we're only going to use for this course 2 inputs, but theoretically they can take more than that. So a variety of logic gates are commonly used in digital computers, and so today we're just going to look at NAND and NOR. Now, what does NAND and NOR actually stands for? Well, NAND is actually just short for not AND. So it's basically taking the AND operation and then not that. In other words, flip the bit. And NOR is basically short for not OR. So it takes the OR operation and it basically nots that or flips that bit. So here's just the summary. So we already know, well, a buffer in this case simply just means whatever the input is the output. But we already know the NOT gate, and so we know that whatever is the input, if the input is 0, then the output will be 1. If the input is 1, then the output will be 0. And same for AND. I'm not going to do all of these. We already know AND, we know OR, and we know XOR. Today we're going to look at NAND and NOR. There's also XNOR or exclusive NOR, which we will just briefly mention, but we're not going to look at that at all in this course. Right, so there's the NAND and the NOR. So remember what I said, NAND is just the same for not AND. So basically, to determine what the output will be for input X of 0 and input Y of 0. Normally for AND, 0 and 0 gives us a 0. And then we have to NOT it or negate it, and not 0 will give us 1. Same for the rest. 0 and 1 would normally give us 0. So NAND of that is going to give us 1. 1 and 0 normally gives us 0, and we NAND that, which basically gives us 1. And 1 and 1 normally gives us 1, and then we negate that, which gives us 0. NOR, similar than not OR. So usually for OR, 0 or 0 gives us normally 0, and then we NOT that, which gives us 1. 0 or 1 normally gives us 1, we NOT that, and that is 0. 1 or 0 normally gives us 1, and we NOT that, gives us 0, and 1 or 1 gives us normally 1, and we NOT that to give us 0. Alright, so that's the 2 extra gates. And then just looking at, we can use the NAND and NOR gates to implement any of the NOT and OR and XOR gates. So today, though, we're just going to show you examples of how we can implement NAND or use NAND to implement NOT and OR. The rest are really done in a similar fashion. We're not going to do it in class here for the interest of time, but really it's done in a similar way. And we're going to try and do that by means of truth tables. So the following table shows how we can implement the NOT gate using only a NAND gate. So just some revision from the previous slide. Remember, a NAND gate, the result of 0, 0, 0 NAND 0 will give us 1, and the rest I'm not going to do at all, but there's the original NAND table. Now, if we basically just take, because remember we want to implement the NOT gate. So remember, the NOT gate only takes one input. All right. So we're gonna see normally with the NOT operation, we know if we take NOT 0, it will give us 1. Or if we take NOT 1, it will give us 0. So to simulate, so to speak, the NOT gate using a NAND gate, we can simply say NAND XX. In other words, you will recall that NAND takes 2 inputs. As you are aware, it takes 2 inputs to be able to deliver us 1 input. So basically, if we take NAND XX, and X in this case, in the first case, will be 0. So NAND 0, 0. What is NAND 0, 0? It will give us a 1. So there is the 1. And then, if we take NAND 1, 1, so in the case here that X is 1, so in other words, we substitute X with 1s, NAND 1, 1, remember what the NAND 1, 1 would give us? A 0. And that basically is exactly the same as that column. So in other words, NOT X produced us 1, 0, and also produced 1, 0 using NAND XX. So in actual fact, we use that NAND gate now to simulate NOT X. Alright, so let's look at how NAND and NOR gates work. So the following table shows how we can implement an OR gate using several NAND gates. Alright, so just for revision, here's the NAND table. So in other words, you're already now familiar with the NAND table, and there's the OR table giving you the OR truth table over there. So for this example, I didn't actually write it out in full, what the entire formula would look like. The actual entire formula would look like the following: NAND of a big thing, and this big thing is not so big. It's actually, again, the NAND. You take the NAND of, basically here, what I call column 1, and that's basically NAND XX. Alright, so we can put that in its own brackets, and then comma, and we do another NAND, the NAND basically here of column 2, which is now NAND YY. Y. Alright, so there you can see this is the actual formula we will use now to simulate how we can use a NAND gate to implement an OR gate. So let's see how that works. Well, here's our normal input variables of X and Y. So if we now take NAND XX, so let's just quickly do this first column. Remember, we're doing that one now, NAND XX. So NAND XX, X currently is 0, so now NAND XX is NAND 0, 0. We just copy basically that 0, it's the same value. So we know by now NAND 0, 0 over there gives us a value of 1. And the next value of x is again 0, so NAND 0, 0, the same result gives us 1. And then if x becomes a 1, NAND 1, 1, as you can remember there, gives us a 0. And again, for that 1, NAND 1, 1 gives us a 0. Let's work out now NAND y. So in the case here, so y in this case is a 0 that we copy. So NAND y is NAND 0, 0, which gives us a 1, as you recall from over there. And then y becomes a 1, so NAND y is NAND 1, 1, which we know on top is a 1. NAND 0, 0 is a 1. NAND 1, 1 is a 0. So now we basically worked out this part and that part. And now we just need to do a final NAND between those two parts, and basically that means a final NAND between column 1 and column 2. So therefore, if we do the NAND of column 1 and column 2, so a NAND of a 1 and a 1, you know by now, gives us 0. All right. And a NAND of a 1 and a 0 gives us a 1. NAND of 0, 1 gives us a 1. NAND of 0, 0 gives us a 1. And now if you look what we have here, this is the actual result for the truth table of the OR function. OR xy, so let's just do OR xy. 0 or 0 gives us a 0. 0 or 1 gives us a 1. 1 or 0 gives us a 1, and 1 or 1 gives us a 1. So there you can see it looks awfully complex now, but we basically only used 3 NAND gates, a combination of 3 NAND gates, and our normal inputs of x and y to actually simulate the same output of the OR function. So just to show it to you, what I've done here, if you actually look at this diagram here, that is a simulation or a drawing of the normal OR gate. So you will remember the OR symbol. It takes 2 inputs. In this case, if it is not colored in, like this gray color, then it means a 0 or off. And if it's colored in like this yellowish color, it means on. So 0 or 1 will give us a result of 1. All right. In other words, it will actually give us the same input as this. So now there's our 3 NAND gates that we've just done in that previous example. First we calculated the first inner NAND gate, the one over here, then the other inner NAND gate, and their result of their 2 outputs. That's the input for the next NAND gate, and that final result actually also gave us 1, which is the same as the OR output. So on the next slide, I just also showed you that the OR gives exactly the same output. All right, let's move over to shifting operations. So what is a shifting operation? A shift operation moves the bits in a pattern by changing the actual positions in the bits. Why do we want to do that? It will become clear a bit later, but for now I'm just going to tell you how they work. They can move bits to the left or to the right. So if you've got 8 bits, for example, those bits can be moved to the left or to the right. So just to try and indicate to you here, so if we have 8 bits here, there we have 8 bits. So what we originally have is basically these 8 bits all stored in 8 memory locations, as you can clearly see over here. Okay, so and there they are, 1, 2, 3, 4, 5, 6, 7, 8 bits. So this bit stream we can actually move to the left. which means the 1 actually moves out of its original 8-bit pattern. The 0 moves into there, the 1 moves into there, and so on. Eventually everything moves over there. And then this very last one seems to go empty because we literally moved everything over. But I'll explain in a bit more detail on the next slides now what exactly happens. There's two kinds of shift operations. And remember, we're going to call this, both of these two operations, we're going to refer to as the first one, the logic shift operations, and arithmetic shift operations. And in turn, you'll see there's going to be two different kinds of logical shifting operations and two kinds of arithmetic shift operations. Let's look at how they look like. So the first, the logical shift operations. So a logical shift operation is applied to a pattern that does not represent a signed number. So it's basically an unsigned number. We cannot do signed operations with logic shift operations. The reason is that these shift operations may change the sign if the number that is defined by the leftmost bit in the pattern changes. So we distinguish two types of logical shift operations. We have a logical simple shift and a logical circular shift. Sometimes we also call this a rotation shift. Let's look first at the logical simple shift. Again, there you will see there's going to be two types of shift, a left and a right, and basically two types of rotates, a left rotate and a right rotate. So let's look at each. So a logical right shift operation basically says we have some original number. Let's make an arbitrary number like this, for example, here. If that was the original number and we had to do a right shift, then basically each of those will move one to the right, and the rightmost one will be lost. And because we moved this one position to the right, there's actually nothing in there. Well, basically we move a 0 into that location. Similar to the logical left shift, so instead of shifting right, we're shifting to the left hand side, and basically also because we're shifting that one into there and this one into there and so on, we shift a 0 into there when we do the shift, and whatever the leftmost one was, whether it was a 1 or a 0, that one will simply be lost. Let's look at some examples. So the example says here, use a logical left shift operation on the bit pattern 10011 and 000. So the solution is shown below. The leftmost bit is lost and a 0 is inserted in the rightmost bit. So here is the original number. So we left shift each original number, as you can see over there, and so on, how those numbers are all shifted to the left, and this original one is discarded. It's thrown away, and there in the rightmost bit a 0 is added in there. So the new, or the result after this shift operation is then 0011 0000. Right, so that is a logical left shift. So let's look, and similar for a logical right shift, I'm not going to do an example there. Now we get to the circular shift operations. Now again, as we said, there could be a circular right shift or a circular left shift. So what the only difference with a circular shift is that nothing is thrown away. So the value in here would be shifted right to there, that one would be shifted into there, and so on. And the right one that was going to be lost is not lost. It is actually moved right over into the front so that it is inserted there into the front. And similar for a left shift, everything is just moved to the left and to the left and so on. And eventually the one that would have been thrown away is not. It moves over into the rightmost block over there. That's a circular shift. Right, so let's look at example 411. Use a circular left shift operation on the bit pattern 1001100. So the same bit pattern again. So it's a circular left shift. So then here is our original number over here, or bit pattern over there. So we left shift everything one to the left, as you can see, basically copying all of those to the left over there, and the one that would have been thrown away moves over to the right hand side over there. Okay. So that is a circular left shift. Circular right shift would have been exactly the same. Now the arithmetic shift operations further, the arithmetic shift operations will perhaps make a little bit more sense to you just now, because currently, I admit, we don't know exactly why are we doing the circular left and circular right and logic left and logic right shifts, but it will become clear later. We're going to use it later. So the arithmetic shift operation, again, as we said, there are two times. The arithmetic shift operations assume that the bit pattern is a signed integer. So for arithmetic operations, we assume it's a signed integer. For logic operations, we assumed it's an unsigned integer. And what's more, it's in 2's complement format. So remember we did in chapter 3, we did 2's complementing. So you must do a bit of revision again to remember how that works. We're going to use it just now. So arithmetic right shift is used to in effect, the result of an arithmetic right shift is to actually divide an integer by 2. That's quite strange. How can such a shifting operation cause an actual correct division by 2? And you'll actually see later that it works in the examples. The arithmetic left shift operation multiplies the integer by 2. But the arithmetic right shift is not so similar than its corresponding left shift operation, because for an arithmetic right shift operation, basically what happens is that the first bit is not moved. It stays there. It makes basically a copy of itself, and then all of the rest are moved and shifted one to the right, and so we go on, move to the right and move to the right, and then the last one gets lost. We throw that simply away in an arithmetic right shift operation. For an arithmetic left shift operation, very similar to the logic left shift operation, we start from the right and we basically copy everyone over to the left until we hear the left one is lost, and we simply insert a 0 on the right hand side of this arithmetic left shift operation. Okay, so let's look at some examples. So in this example, use an arithmetic right shift operation. So we know by now right shift arithmetic operations divides an integer by 2. So do that right shift operation on this bit pattern over here. The pattern is an integer and it is in 2's complement format. So you know it is valid we can do arithmetic right shift operations with this bit pattern, as we assume that it is an integer and in 2's complement format. Okay, so the solution is below. So remember, for a right shift, we basically copy the first one back into the first, and then from there we do a right shift of everything else. The 1 moves into there, the 0 moves into there, and so we go on, and the rightmost one, that one, is simply discarded or thrown away. So let's test this. Let's make sure this is in actual fact correct. This original number over here, this 1001101, that actually represented minus 103. So let's do a little bit of revision for 2's complementing. Remember, in a 2's complement number, if the first value is a 1, we know it is going to be a negative number. All right. And then how do we go about further? Well, we start from the right and we start copying each value until we get a 1. So the very right number is a 1, and then we stop copying over there because now we found a 1. What do we do next for 2's complementing? We simply take the remainder of this number and we do a 1's complement, in other words, but flipping. So the 0 becomes a 1, the 0 becomes a 1, the 1 becomes a 0, the 1 becomes a 0, 1, 1, 0. And we now take this number here and we simply convert that to a positive decimal number. So we know already that value is going to be 1, 2, 4, 16, 32, 64. So 64 plus 32 plus 4 plus 2 plus 1 actually gives us 103. And remember, it was a negative because the first value was a 1. All right, so the original number was indeed stored in 2's complement format, and it was minus 103. Now, by doing this arithmetic right shift, we get this value over here, which is 11001100. And let's see if we now convert that into a decimal integer. So again, the first value is a 1, so we know it's negative. Therefore, the procedure is start from the right hand side and copy until we get a 1. It's a 0, so we copy it. It's a 0, so we copy it. It's a 1, so we still copy it, but we stop there. The remainder we simply do bit flipping, so the 1 there becomes a 0, the 0 becomes a 1, 0 becomes a 1, 1 becomes a 0, 0, and we now take this value over here and we convert it to integer. So this is 1, 2, 4, 8, 16, 32. So 32 plus 16 plus 4 actually gives us 52, but remember it was originally a 1 over there, so therefore it must be minus 52, and that's exactly what we get there. If you take 103 minus 103 and you do an arithmetic right shift operation, we know we're going to divide by 2. Now, minus 103 divided by 2 is technically minus 52.5. But we are doing here what we call integer division. So the 0.5 is simply thrown away, which basically leaves us with the final result of minus 52. Very clever. Right. So this is an arithmetic right shift operation, which in effect is dividing a number by 2. Doesn't matter if this number was positive or negative, as long as it is an integer stored in 2's complement format. Let's look at the next example. So this example, use an arithmetic left shift operation on this bit pattern over there. So again, we know it is in a 2's complement format. So doing a left shift arithmetic operation is almost the same procedure as a left shift logic operation, which means we basically shift everything to the left. The 1 is shift over there, the 0 over there, and so we go on, the 1 over there. This one here, we simply throw away. And the rightmost bit that's now empty, we simply add a 0 over there. Alright, so now what in effect this is, you can go and do the math again. I'm not going to go and do it for you, but go and calculate what is the 2's complement value of that. You will find out it's going to be minus 39. And if you calculate the 2's complement value of that, you're going to find it's going to be minus 78, or is it going to be 78.5, I think. But basically, that is in effect what has happened. We have multiplied, we've multiplied 39 by 2. So there's not going to be a 0.5 involved here, sorry about that. So 39 multiplied by 2 minus 39 times 2 gives us minus 78. Let's do another example. Use an arithmetic left shift operation. So an arithmetic left shift, we know we're going to multiply by 2 in effect. Same procedure as the previous example. Move everything 1 bit to the left. So we go on until there. This 0 gets thrown away. And we add basically a 0 over there in the last bit. So again, if you go and calculate the arithmetic, the 2's complement value of that, we'll find that it's going to be 127. Now that we did this, if you go and calculate what this value is after the shift, you get minus 2. And we just said we're doing a left shift operation, so we know we're going to multiply basically 127 by 2. And now we get minus 2, which is not what we expected. And the reason for that is that an overflow has occurred. We will need more bits, because we know 254 is the real correct value that we should get here, but unfortunately we only use 8 bits. All right, so and 1 bit is the sign, so which basically means that 127 is the actual maximum number we are able to store in there. If, by the way, if originally this was a 1, it would have meant minus 127. Right. So, but now we know we cannot store that. We will need an extra bit if we want to do a shift operation for that to still have the correct value. All right. So now we can start combining the logic operations that we discussed earlier, you know, the AND and OR and NOT and NOR and NAND and XOR and so on. We can start combining those with logical shift operations. And let's see how this is going to work. In this example, assume that we have a pattern and we need to use the third bit from the right of this pattern in a decision-making process. So what they're saying, let's assume here we have a bit pattern labeled basically from right to left, A, B, C, D, E, F, G, H. Whatever there is in A to H could either be zeros or ones, right? And we want to try and find out what is the third bit from the right. In other words, what is stored in C. Where do we want to know this kind of thing? Well, typically when we send data over a network or wherever, we might want to send some information. This bit pattern, for argument's sake, might hold the information of 8 lights that are either switched on or off. So for example, if the content was 110110001 as an example, then it simply meant that there's 8 lights. This light is on, that light is on, that one is off, on, off, and on. So that is typically, practically, how such an implementation can work. Now we want to basically know, is light C, or the third light from the left, is that switched on or off? Okay, so what we do is we're going to do some logic right shifts. So this is actually, we can say, it's a one logical right shift that we see over here. Which this simply means, if you remember from the right shift, we shift everything just one to the right, and so we continue, and the rightmost one, the A, just basically falls off. Then we do yet another logic right shift. So again, everything moves to the right, and so we basically have C, the one we want to look at, on the right hand side. So that's an assumption we make here, that the mask that we see over here is created so that it checks only the rightmost bit. And if we do an AND mask where only the rightmost bit is 1, then it's basically going to try and AND the rightmost bit. So remember, we're not interested in what's going on in the 7 leftmost bit. It's only the rightmost bit, and for that reason the mask on the right hand side is only a 1. So the result will be basically all of those will be made 0, because 0 and anything will always result into a 0. And now, depending on what is C originally was, as over there, was a 0. So 1 and 0 will give us a result of 0, so we know the light is switched off. If we simply now convert this entire binary number, this result, into a decimal value, it gives us 0. And in other words, the result is 0. If it was on, it would have been 1 and 1, which resulted in a 1. Converting this entire thing into a 1 will give us then basically a 1. Alright, so now you see we've used a combination of logical right shifts and a mask in this case, and then also the logical AND between each of the bits, and eventually the last one of the mask is a 1, which will give us a 1 result if C was a 1, or a 0 result if C was a 0. Right, so that's the end of this lecture. Please make sure that you go through this lecture, and I'm not going to, in Thursday's lecture, give opportunity like on Monday to first look through the slides. It's only going to be a question and answer session during that session. Thank you very much, and enjoy the rest of your day.